Today we're going to be reviewing Chapter 4.1, the Extreme Value Theorem, and the extremas. So there are two types of extremas, absolute extremas and local extremas. First, we're going to be talking about the definition of the absolute extrema, or extreme value. The first definition, it states, if f of c is less than or equal to f of x, then f of c is the absolute minimum. And a note to add is f of c must be the lowest y value in a given function to be the absolute minimum. And the second definition is if f of c is greater than or equal to f of x, then f of c is the absolute maximum. And another note to add is f of c must be the highest y value in a given function in order to be the absolute maximum. There's a condition to consider, and it's that f of c must exist or be defined. So if there's a test question that asks explain, and it's relating to absolute extremas, then you can say f of c must exist or be defined, and that'll save you from getting a point off on the test. Now the definition of a local or relative extrema, and those are the hills and valleys. And the first definition says, if f of c is greater than or equal to f of x when x is near c, then c is a local maximum. If f of c is less than or equal to f of x when x is near c, then c is a local minimum. And there's a key difference between the definition of an absolute extrema and a local extrema. And it's that the absolute extrema is when x is at c, whereas the local extrema is when x is near c. So keep in mind of that. And we talked about it in the notes, but the notes didn't directly state this, but here are three notes that weren't stated in what we went over. And it's that keep in mind that wholes aren't considered minimums or maximums. Endpoints of an interval are not considered local minimums or maximums unless if they are absolute minimums or maximums. And the last one is absolute minimums or maximums are considered local minimums or maximums if the derivative of f of c is equal to 0 or a hill or valley. And I'll go over these notes on an example that we're going to look at. So find the absolute and local extremas. So we said in the definition of an absolute extrema is when f of c is the highest y value of f of x for the absolute extreme, for the absolute maximum, and f of c must be the lowest y value for the absolute minimum. So looking at the graph, it's separated by the intervals of 2. So we're going to be approximating around here. So for the absolute maximum, we're going to approximate about -4.5 and 6. That is the highest y value, so that will be the absolute maximum. And about 5, -6, that is the absolute minimum because it is the lowest y value within the function f of x. In local extremas, we said that they are the hills and valleys. So looking at -2, 0, that's a valley, so we can say -2, 0 is a local minimum, and 2, 4 is a hill, so we can say 2, 4 is a local maximum. And looking back at the note that I said, the first one says wholes aren't considered minimums or maximums. So let's say at -4.5 and 6, if that was a whole, then that would change this answer here, the absolute maximum, to change to be does not exist. And so that is referred to wholes aren't considered minimums or maximums. The second point that I added was endpoints of an interval are not considered local minimums or maximums unless if they are absolute minimums or maximums. So that's a bit wordy, but I'll simplify it. And to show it, it's that, so as you can see, let's say if negative 4.5 and 6 was not considered an absolute maximum. Let's say the interval was shortened to about negative 3 and 2, about negative 3.5 and 2, then let's say it would start about right there. And then we're not considering this part here. So let's say if that was the new interval, then that would change 2, 4 to be the new absolute maximum. And then this here, I said on the second point, endpoints of an interval are not considered local minimums or maximums because what we stated for the definition of the local extremas is that they are the hills and valleys. So if it's starting at an endpoint and it's not an absolute extrema, then it is not, we are still not considering it to be a local extrema as well. And the last point I said was absolute minimums and maximums are considered local minimums or maximums if the derivative of f of c equals 0 or makes a hill and valley. So let's consider, let's say this graph changed to be this. Let's say the graph extended its interval. As just by looking at it graphically here, this would be the new absolute maximum, and over here this would be the new absolute minimum. And that would make this statement true because the derivative at f of c is 0. So that would make it a local minimum because it makes a hill or valley. Same with the absolute minimum. It makes a hill, it makes a valley, so that, and the derivative of f of c equals 0. But when it's not the case, looking back at the original graph, the absolute maximum is negative 4.5 and 6 and 5, negative 6. But it does not make a hill or valley, so that is why we do not make 5, negative 6 to be a local minimum and negative 4.5, 6 to be a local maximum. And the last topic to cover is the extreme value theorem. If f is continuous on a closed interval a, b, then f has both an absolute minimum and absolute maximum. And there's a condition for this theorem, and it's that f must be continuous on the closed interval a through b. Looking at an example, find the absolute extremas. Well, looking at the graph, you can see that the hills and valleys all are holes. So we can say that they do not exist, as I stated on the note to add, holes are not considered minimums or maximums. So we can write it as absolute minimums does not exist, and same with the absolute maximums. If you were to write it in a sentence, f of x does not have an absolute minimum or absolute maximum because f of x is discontinuous. That is the end. Thank you.